Um, I'm audible, right? Okay. Yeah. So, hello and welcome to the final week of the NPTEL MA106 category theory course. So, this week you learned about some topos theory, or maybe the basics of topos theory. And as you might have understood by now, that toposes are like, I mean, the best categories in the sense that they have a, I mean, even though the definitions are pretty simple, but the properties that they uh, admit are really, I mean, it's really incredible. So toposes are like the nicest categories with which one can work with. And uh, so I mean, the literal meaning of the word topos is space. And I mean, I'm sure you have already seen that there are various different ways to interpret a topos. And in fact there are, I think, at least 15 different ways to interpret the notion of a topos. But this week, as far as I have understood, there were two special kinds of toposes that were introduced. And those are, just a minute, yeah, elementary toposes and grothendieck toposes. So the motivations for considering these two are quite different. On one hand, elementary toposes were principally due to Laurier, and maybe much later due to Tierney as well. While grothendieck toposes were, as the name suggests, due to Alexander Grothendieck, who sort of, I mean, it's said that sort of changed the entire face of algebraic geometry once he came up with the notion of a Grothendieck topology on a category. So I'll briefly mention things that were covered this week. Again, thanks to Pranay. So, and then we'll solve some problems. By the way, I'm Shubhajit Das. I'm a PhD student at the Department of Mathematics, ISC. So, yeah. Okay, so was classifying toposes also covered this week? Or was it just an introduction? Okay. So classifying toposes again have motivation in logic. I am not really well versed with mathematical logic, or at least as much to appreciate what classifying toposes really do. But classifying toposes are actually related to mathematical theories. So it's so there's this theorem which says that given a mathematical theory, there is some classifying topos together with some object in it, such that if you look at models of that theory in an arbitrary topos, then those are exactly the same as looking at geometric morphisms from that arbitrary topos in which you are taking models to the classifying topos. So we'll not focus on classifying toposes, but as mentioned, we'll talk about elementary toposes first, which was essentially due to Laurier. So you learnt about elementary toposes. I'll just write down Laurier, and I should also mention well, there's a good reason, I'll get to it. So the point is, and this is really interesting, that toposes do have something called an internal logic and an internal language. And very crudely speaking, I mean, this is not exactly correct what I'm saying. I mean, some extra things need to be said. But the idea is, whenever one looks at toposes, what you think of it, or you can sort of, whenever you look at it, so what is that elementary topos? It's a category with objects, arrows, as always. I mean, it's a category which has which is finitely complete and has a sub-object classifier and is Cartesian closed. The interesting thing is that, naively speaking, you can think of a topos as the category of sets, and the objects of a topos, you can think of them as sets, and the arrows of a topos, you can think of them as set maps. So whenever you try to prove something, and I am sure you have already seen many things about toposes, many properties of toposes which resemble properties of the categories of sets. So whenever you try to prove some statement, again this is a very crude way of saying it, but whenever you try to prove some statement or some property in a topos, the basic idea is to think of all the objects as sets and arrows and as maps. So literally you can argue using elements, and it's, very roughly speaking, if it holds in the category of sets, then subject to certain conditions, it will also hold for that topos. So that is why elementary toposes are so called, because you can argue with elements, roughly speaking. So this is all phrased in terms of the internal language of a topos. And just quickly tell me, what is an elementary topos? So an elementary topos. Okay. So it's a category with finite limits. I am sure that I can't, so finite limits, and we can say, I'll put this in brackets, I'm sure he has covered this, that, so this is really interesting about a topos, that if it has finite limits, then you can actually prove it also has finite co-limits, which is like a really interesting property for a category to have. What else? It is Cartesian closed. So quickly, can you tell me what is the definition of a Cartesian closed? Can you recall it? Yeah. No, it has a right adjoint, right? Because you keep this mental picture in mind, that the tensor for modules is left adjoint to the Hom for modules, right? So likewise for Cartesian closed, so whenever we say Cartesian closed, it means that so closeness is always with respect to some monoidal structure. Here the monoidal structure is products, and analogously you think of taking products as the left adjoint, and it is supposed to, if it has a right adjoint, then you say that the category is Cartesian closed. So I'll briefly write that for every, we have already assumed existence of finite limits, in particular finite products. So for every object A in your category is a category C, let's say. In fact, the better notation is to write E. For every object A in E, taking products with A, which is a functor, the direction is from E to E, has a right adjoint. And this right adjoint functor is usually written as this. Okay, so this is our second property. Again, Cartesian closeness is very interesting, and in particular, if some taking products with some object A, if suppose A is a fixed object, and suppose taking products with A has a right adjoint, then we also say that the object A is exponentiable. So equivalently, you can also say that an elementary topos has exponentials for every object. And number 3 is has a sub-object classifier. Again, sub-object classifiers, even though might not be really very what should I say, relevant as far as geometry etc. is concerned, but they are really important for in logic theory, or so as I have been told, or have I read, maybe. So as a sub-object classifier. Okay. So what is a sub-object classifier? Yeah. Okay. Yes. Correct. So a subobject classifier is something that essentially characterizes subobjects of any object in the sense that it is a monomorphism which is universal in the sense that every arbitrary monomorphism in your category is uniquely a pullback of it. So what is it? It's a monomorphism which is classically written as true from 1, where 1 denotes the terminal object of your topos, to omega for some object omega, which we think of as the object of truth values. Okay, so I have a call, I need to take this. I'm sorry. I'll resume in 2 minutes. Hello. 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 Yes, you called me just now. Oh, I am not in MS. I am actually teaching right now. Can you leave the package behind and send me the QR code? So, in A block. Payment you send me the QR code. Yeah. Yeah. So send me the QR code. I'll pay it and. Yeah, I'm disconnecting the call. I'm teaching right now. Yes. 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 Okay. Okay. Yeah. Sorry for the interruption. Yeah. So it's a subobject classifier is a monomorphism where omega is considered as the object of truth values. So in a sense, I mean, even though objects in abstract categories don't have elements, there is no notion of internal data or internal structure for objects. Objects are the ground concept, they are the primitive notion. But we can think of a map going into an object as some kind of generalized element of that object. So a sub-object classifier in this way is essentially a truth value of omega. And in addition, you should have, the map should be a monomorphism such that for every monomorphism A prime to A F, there exists a unique arrow A to omega, which we think of as the characteristic morphism of the subobject A. Let's call it chi F, such that the following is a pullback square. So what is it? A prime A omega chi F 1 to omega. This is your true map. This is the unique arrow. This square is a pullback square. Yeah, so this is a sub-object classifier, and once you assume these three properties for a category, the category is called a elementary topos, and you can prove a number of interesting things about them. So we won't get into the details of all this. I believe all this was covered. What else? Okay, we will quickly skip to the sheaf theory part, or rather the Grothendieck toposes, which was the content of your last lecture. So by the way, examples of elementary toposes are pre-sheaf categories in particular. They are like the largest class of examples of elementary toposes, and there are other elementary toposes like continuous actions of a topological group, etc. Which, I mean, categories which are not pre-sheaf categories. So okay, so I believe this was also covered in particular. I mean, this example that I just discussed was discussed in more detail. So pre-sheaf category, pre-sheaves on a small category, and so I mean I believe you have all of this was proved this week, but just to quickly recall, pre-sheaf categories are already complete and co-complete. So in particular, finitely complete, that is Cartesian categories. So the first property is satisfied, and pre-sheaf categories are Cartesian closed. The trick is to use to guess the definition of what an exponential should be, you use the Yoneda lemma. And 3 has a sub-object classifier. So what is the sub-object classifier for a pre-sheaf category? You can hear me, right? Yeah. Yeah. Okay. So I'll quickly recall it. So suppose that omega, at least the object part, omega, so it should be an object in the pre-sheaf category. So pre-sheaf category, let's say C op comma set, where C is assumed to be small. I'll just write it in brackets, C is small. You can actually do it not just for small, you can actually talk about all these things once you have fixed your own set theory and assume some kind of axiom, size axiom. So everything is relative to some universe. So for now, we just mentioned that C is small, and to consider a presheaf category C up comma set. So omega should be an object in this presheaf category, so it should be a functor C up to set. Now, what is this functor? We want to know what this functor does or what this functor is, right? So in particular, for every object C, we want to know what omega C is. Now, sub-object classifiers have a universal property. I mean, the way they were introduced, it's apparent that they have a universal property. But there is a better way in terms of representability by which you can use sub-object classifiers. So can you quickly recall what that is? So if your category has finite limits, then you can consider this functor sub C from C op to set, and assume that your category is well powered as well, in the sense that for every object the class of sub objects is indeed a set. Then you have this functor sending every object A to its class of sub objects, set of sub objects, B to set of sub objects, and if you take an arrow A to B in C op, we'll denote it by F op, which means F is an arrow B to A. Then you have an arrow sub C A to sub C B given by taking pullbacks. So let's just call this arrow, denote this image arrow by sub C F op, let's say. What does it do? So take a sub object of A. You have an arrow from B to A in your category, and you can take, since pullbacks exist, you can take this pullback. And since pullbacks of monos are monos, so this pullback object will be a sub-object of B. This is your functor. So if a sub-object classifier exists, in fact a sub-object classifier exists for such a category if and only if this functor is representable, and its representing object is your omega. Okay, so what, in other words, what we have is sub C is naturally isomorphic to C of gap comma omega. It's a representable functor, contravariant. So this is what it is. Now, what does this mean? This means that sub C of A for any object A is in biject. This set is in bijection with this Hom set from A to omega, and this is happening naturally in the object A in your category. Yeah, what do we want? We want what omega should be, right? Okay, so yeah, some small mistake in notation. So sub should be a functor from, yeah, I'm sorry. Here the category that we are concerned with is not C op. It is C op comma set op to set. Yeah. So I'll just write sub. So A, B, everything is a presheaf here. So this is not C. This will be the presheaf category. So presheaf categories are commonly introduced by C hat. We'll just write C hat for, commonly denoted by C hat. So C hat will denote C op comma set, this presheaf category. Okay, so yeah, so this is what it is. Now, what I want to know is, what is this omega, right? So omega, which is a functor C op to set, should act on an object of C. And what is this by the Yoneda lemma? Do you know an expression for this? Omega is a presheaf. Omega acting on C. This is what is this set? What does the Yoneda lemma say? It is in bijection with No, this is our set. But what does the unit lemma say? Omega is a functor. So omega is a functor. Yeah. So omega c should be in bijection with the set of natural transformations, right? So it should be in bijection with the set of natural transformations from the functor represented by C to omega, right? This is what the unit lemma exactly says. Okay. So omega c is in bijection with the set of natural transformations yc to omega. And what is this by our representability property for omega? This is exactly sub of yc. So in other words, so omega c is a set. The elements of omega c will be sub-functors of yc. And we have, I'm sure while discussing Grothendieck toposes and sheaves, etc., this was already introduced. And this is actually called every sub-functor of yc is called a sieve. So this is actually the set of sieves on C. So omega c can be defined as a set of all sieves on C. So in this sense, sieves on objects form the sub-object classifier of your pre-sheaf category. Okay. And then interesting things were introduced, primarily the notion of a Grothendieck topos. So what is a Grothendieck topos? Well, there are again various ways of introducing this. One way is to say it's some category which embeds along a geometric morphism into a pre-sheaf category, etc., etc. And since the category of sheaves, so the category of sheaves on some topos actually has a very nice characterization, in the sense that if the sheaves are taken over a small category, then the category of sheaves is actually a localization of the category of pre-sheaves. So there are various ways of characterizing this. The usual way is first to define what a site is. So what is a site? It's a category equipped with a Grothendieck topology. And then once you have a notion of a Grothendieck topology, you can talk about what a sheaf is. And a Grothendieck topos is then defined to be some category which is equivalent to category of sheaves on some site. So we won't discuss all this in details, just mention the exact map of this. So firstly, sieves are introduced. We already saw what are sieves. Sieves on an object are subfunctors of the functor represented by that object. Then the notion of a Grothendieck topology is introduced. So what is a Grothendieck topology on a category? So a Grothendieck topology on a category is exactly a function that assigns to every object of your category a collection of sieves on that object in such a way that certain axioms hold. Firstly, the maximal sieve should be in that collection. Secondly, something called stability holds. And thirdly, something called transitivity axiom holds. I'm sure all this was covered this week. What I cannot find here in this list is, so sometimes it happens that, so just as for topological spaces, it's not always ideal to work with the entire topology of a topological space. Rather, people can often work with something called a basis for your topology. Similarly, for Grothendieck topologies as well, it need not be the case that you need to work with topologies all the time. Rather, you can work with something called a basis for your topology, which is sometimes also called a pre-topology. And at least algebraic geometers only work with pre-topologies. So whenever they say they are working with a Grothendieck topology, they actually mean they are working with some basis for that topology. So I'll just roughly mention basis for a Grothendieck topology. Handling bases are, it's much more convenient to handle bases. compared to the entire grothendieck topology. So what is the basis for a grothendieck topology on a category? So on a category C, let's say small category, so it is exactly a function that assigns to each object. So a function, let's say B, that assigns to each object A of C a collection AC, BA of class a collection BA of families of morphisms with codomain A or into A. So each such family will be called a covering family, or a cover or a K cover, a B cover to be very precise. Families of morphisms into A such that firstly, so such that three axioms here also hold, and they are supposed to mimic the usual axioms for a grothendieck topology. So firstly, every singleton isomorphism. So what I mean by this is a family with exactly one member in it, which is an isomorphism. So every singleton isomorphism, let's say from some object to your object A, is in BA. Secondly, you have something called the stability axiom, which actually talks about stability under pullbacks. I'll not mention it, you can check the details. And then you have something called transitivity axiom. So stability axiom is concerned with pullbacks. Okay. So in other words, if you take a covering family for an object and take an arbitrary arrow in your category, which goes into that same object, then you can form pullbacks, and the pullbacks of the arrows in this family, if you look at the collection of pullback arrows, then that will be a covering family for your for the appropriate object. So it's something like, it's supposed to capture base change in a very rough or crude sense. So stability axiom is concerned with pullbacks, stability under pullbacks, and transitivity axiom is supposed to capture what is it going to capture? It's supposed to capture well behavedness with respect to compositions of arrows. Okay, so what it essentially says is that if you take a cover for an object A, and for every domain, and if you look at every arrow in that cover, look at the domain. For that domain, if you take a cover, then the compositions, once you take the compositions of all these arrows, that will again be a cover for A. Okay, so this is the idea of a basis for a grothendieck topology on a category, and every basis for a grothendieck topology, as the name suggests, should generate a grothendieck topology. There's a definition for that as well. Now, interestingly enough, the sheaf condition can actually be expressed in a better way, I would say, with respect to basis for a grothendieck topology. You have already seen sheaves on topological spaces, which are exactly pre-sheaves satisfying some gluing property. The definition can be entirely expressed in terms of a equalizer diagram. Then you have seen sheaves for a grothendieck site, sheaves on a grothendieck site, right? So they are exactly pre-sheaves on the base category, which satisfy some analog condition of the gluability axiom, and you can also express it entirely in category theoretic terms. So I would say that I'd say that a presheaf F on C on a so suppose C is a small category equipped with a grothendric topology. This pair is called a grothendric site, and suppose F is a functor from C up to Z, that is a presheaf on C. I'll say F is a sheaf if for every object C in C and for every covering sieve, let's say S in JC. So S is a J cover for C. S is a sieve on C, and this S is a member of your coverings, of the family of coverings. So for all S in JC, so what is S? Recall, S is exactly a subfunctor of C, a subfunctor of the functor represented by C, right? So there is a monomorphism from S to YC, right? So this is a monomorphism, and I'll say F is a sheaf if every natural transformation from S to F, everything is a functor here, the arrows are there for natural transformations, can be uniquely extended to an arrow from YC to F. Okay, this is what the sheaf condition says actually. And I mean, if you go deeper with the definitions or try to unwrap them, you'll exactly see that this mimics the notion of the gluability property for ordinary sheaves on topological spaces. So a natural transformation from a sieve to a presheaf is exactly something called a matching family of for the sieve of elements of F. And what this says is that if you take any arbitrary matching family, then you can uniquely extend it to a functor from YC to F. I mean, sorry, to a natural transformation from YC to F, which by the Yoneda lemma is exactly some element of FC. So every matching family has a unique amalgamation. That is what it says. This is your sheaf condition, right? When it comes to basis for a grothendric topology, again this condition can be simplified in terms of a equalizer diagram. So for ordinary sheaves, when you talk about sheaves on topological spaces, what is your equalizer diagram? So you take, so a presheaf on a topological space will be called a sheaf if for every open cover of your of some open set in your topological space, Fu is the equalizer of that particular diagram, right? We don't want to mention it. What I only want to mention is in that diagram you talk about intersections, right? Intersections of open sets. What should be the categorical analog for intersections in an arbitrary category? Yes. So instead of taking intersections, you want to talk about pullbacks. So you can also, yes, every grothendric topos can be proved to be an elementary topos, but not conversely. Every grothendric topos is an elementary topos. You can prove this explicitly. I mean, for some properties at least this is very clear, right? For example, why would you say that the category of sheaves, for example, is, let's say, finitely complete? Because the category of presheaves is finitely complete. I mean, it's complete only. It's finitely complete, therefore. And the category of sheaves is a reflective subcategory, right, of the category of sheaves, of the category of presheaves. So what is a reflective subcategory? Can you quickly recall? No, the inclusion functor is a right adjoint. It has a left adjoint, right? So if you forget, always keep the picture of AB and GRP in mind. The inclusion functor from the category of abelian groups into the category of groups is a right adjoint. It has a left adjoint, which is the abelianization functor. Keep this in mind. So the category of abelian groups is a reflective subcategory of the category of groups. And this adjunction between these two functors is called a reflection. So the category of sheaves, because we know that or because sheafification can be, the existence of sheafification can be proved for arbitrary small growth ending sites. So sheafification is a left adjoint to the inclusion. So the category of sheaves will be a reflective subcategory. It's a full subcategory, and the inclusion functor is a right adjoint. So it can be proved to be a reflective subcategory. And what do we know about reflective subcategories as far as limits are concerned? Do you know something? No, that's not always true. That's a different thing. That is something called a localization. But what we know is, this is what we know about reflective subcategories is that, suppose you take a diagram in your reflective subcategory, and suppose you think of this diagram as a diagram in your big category. If this diagram in your big category has a limit, then this diagram in your subcategory will also have a limit. That is what it says. Okay. I mean, the limit can be exactly computed as if you are working in the big subcategory, a big category, and not the subcategory. This is not true for co-limits, but this is certainly true for limits, for reflective subcategories. So computing limits in reflective subcategories, you can actually compute them as if you are in your big category. In other words, reflective subcategories inherit limits. Okay, so the category of sheaves is finally complete, has a subobject classifier, has exponentials, etc., etc. It will be a grothending. It will be an elementary topos. So every grothending topos is an elementary topos. But the converse is not true. There are examples. For example, there's this example of something called an effective topos, which was introduced by Johnston, I believe, Peter Johnston. And you can sort of simplify, I mean, you can give simpler examples of this. For example, the category of finite sets will be a elementary topos but not a grothending topos, because it will not be complete or co-complete. Okay. I'm sorry. Sorry, I'm getting a lot of calls. Yeah, I'll quickly mention the topics. So grothending topology, grothending site, sheaves on a site, grothending topos, and then there's this interesting thing called Girod's theorem, which is like a characterization theorem for grothending toposes. I won't mention the theorem, but what it says, so see, the point is, sometimes working with grothending toposes can be a bit difficult, in the sense that the way they are introduced is exactly that you should, so to find out whether a category is a grothending topos, you need to come up or construct or show the existence of some site whose category of sheaves is exactly equivalent to your category. Then I can say my category is a grothending topos. So working with such a thing might be a bit difficult, but we are safe due to Girod's theorem, which gives a characterization of those categories which satisfy a bunch of axioms, or rather a bunch of properties, to be to be characterized as a grothending topos. The properties are exactly category theoretic in nature, and it turns out that a category having those properties is exactly equivalent to the category of sheaves on some site. So that is what Girod's theorem says. Yeah. Let us quickly jump to the problems. Okay. So we'll start with our first problem, which says that, and this is something we have already mentioned but didn't prove, Suppose that C is a well-powered Cartesian category. So we know what a well-powered category is. For every object A, the class of sub-objects of that object is a set. And Cartesian means that it is finitely complete. It has all finite limits, in particular finite products. Now we can certainly talk about this sub-object functor. Firstly, because it's well-powered, and secondly, because pullbacks exist, we can talk about the sub-object functor, sub from C up to set, right? And suppose that this sub-object functor is representable. What we need to show is that C has a sub-object classifier indeed. So we can fully understand what that sub-object classifier is. That will exactly be the representing object of your functor sub. So suppose that sub is naturally isomorphic to C of gap comma sum omega. Okay. What we want to show is that omega has the structure of a sub-object classifier. So in particular, we need to find out a monomorphism from 1 to omega, right? So let's look at the most natural thing to do right now, which is look at the identity map from omega to omega. So consider the identity arrow from omega to omega, right? Because sub is representable by omega, so elements of sub omega are the same as arrows from omega to omega. So in particular, the identity morphism from omega to omega corresponds to some element. This corresponds under the bijective map from sub omega to C omega to omega to some sub object, let's say omega 0 to omega. Now what do you think omega 0 should be? What do you think omega 0 should be? Are you there? What do you think omega 0 should be? So to some subobject, let's say m omega 0 to omega. So we claim that omega 0 is the terminal object. Of our category. So how do you show this? Yeah, so we claim that omega 0 is the terminal object of C. How do we show this? We already know that C has a terminal object. How do we show that omega 0 is the terminal object? Okay. But that would only prove existence of, at most one, right? That won't prove existence as well. we can directly try to show that 1 is isomorphic to omega 0 as well, right? So how do we show this? So we have C has a terminal object because our category C is Cartesian, right? We have assumed that. By the way, why is this the case? Why is existence of finite limits? Why does existence of finite limits imply Cartesian? I mean, imply it has a terminal object. In particular, why does existence of finite products imply that it has a terminal object? Because the terminal object is a limit, right? Of what the shape, limit of a diagram of what shape? Sorry. Yes. So it has a terminal object, one that we know. So we consider or rather we also consider the arrow (1 to omega) corresponding to the sub-object. So this will, and whenever we are saying corresponding to, we'll always we are always meaning that we are doing things with respect to this natural isomorphism or component, or the component of this natural isomorphism at some object. So here the object is 1 at which we are considering the component. So this will correspond to some sub-object of 1. So what sub-object? We are taking the identity arrow, let's say I11 from 1 to 1. Yeah. So you consider this morphism. This is a morphism in C. Okay. So let's quickly, I mean, even though the notations might be a bit confusing, but what we have so far is, firstly, we have a map from omega 0 to omega, and we have a morphism from 1 to omega. So see, we wanted a morphism from 1 to omega, and since this morphism corresponds to identity map on 1, we can very well imagine that this morphism 1 to omega is exactly our morphism that we want, right? So we can instead try to show that there is some isomorphism 1 to omega 0 which makes the relevant triangle commute. So using M, this arrow 1 to omega, and the isomorphism 1 to omega 0. So my point, what I want to say is we want to relate these morphisms. So we have a morphism. So we have firstly a morphism omega 0 to omega M. We have a morphism 1 to omega. Let's call it T. We want to relate these two morphisms. So what can we do? Can we use, I mean, we haven't really used the fact that we have a natural isomorphism. So let us try to use naturality here. So what does that mean? What does naturality mean? So suppose I want to talk about, use the naturality with respect to this arrow 1 to omega t. So what would that mean? That means that, so for the morphism 1 to omega t, the following diagram commutes. What is the diagram? Yes, sub 1 to sub omega. This is sub is a contravariant function, right? It will be in the opposite direction, right? Sub omega to sub 1. This is sub t. right? And sub 1 to omega, C 1 comma omega. This is our isomorphism, the component of the natural isomorphism at 1, and this is the component of the natural isomorphism at omega. And from here to here we just have, so omega to omega, 1 to omega, 1 to omega comes first, so this, right? This square will commute. So we start here, take a subobject of, we want, the point is we want to relate this to, so start with sub omega. By the way, this is not the only way in which this should have been done. I mean, you can try some other way as well. Work with a different morphism or use naturality with respect to some different morphism as well. It just might as well work out. I mean, this approach that we are taking. So take some subobject of omega. I mean, we have already fixed a subobject of omega, which is omega 0 to omega m. Take this subobject. By definition, this gets mapped onto the identity on omega. That is what it corresponds to, which gets mapped to t from 1 to omega. On the other hand, from so what is this arrow? So you have omega 0 to omega m, and you have 1 to omega t. You just take the pullback. Let's say, how do you write the pullback here? Okay, so omega 0 crossed over omega with 1. You take this pullback. So from this to 1, you have an arrow. You have a subobject. So omega 0 crossed over omega with 1 to 1. You take this subobject of 1. Under the isomorphism, it should get mapped to t, right? That is what it says. Now, what do we know about t? How was t given? How was t defined? So t was that morphism which corresponds to the subobject 1 to 1, the identity, right? Now this map is a bijection, right? T is that morphism which corresponds to the identity the subobject 1 of 1, right, with the identity map. And what we have shown, because this diagram commutes, what we know is that this subobject corresponds to T. The map is a bijection, in particular an injection. So what can we say? Okay, let's skip this. So omega 0 crossed over omega with 1 to 1. This is the, okay, something is wrong. I don't know why, but okay, we'll see. Is the subobject, is this equivalence class is exactly equal to the equivalence class 1 to 1 identity. Yeah, these two are the same, right? Something is wrong. We are not. Yeah. I guess we need to work with the map, with the unique map omega to 1 and use the naturality of that. Let's quickly see what if we worked with the unique map omega to 1. No, that won't make much sense. Yeah, do we know something about this pullback? omega 0 times over omega with 1. Something is wrong here. So omega 0 to omega, we have m. I mean, what I'm saying is we have only proved that omega 0 times over omega with 1 is the same as 1, but we didn't prove that omega 0 is isomorphic to 1. Wait. Okay, something is wrong. I'll figure this out later. Let us not waste time. I mean, this is easy. This is supposed to be easy. We probably didn't take the right things in this. This should be solved, I mean, just by using naturality. We'll come to this. Let us not waste time. Let's move to the next problem. Suppose Cj is a site, and suppose that S is a J cover for an object C, and suppose R is a sieve containing S on the object C. What we want to show is that R is in JC. So what this essentially says is that if you look at JC, the collection of all admissible sieves on C, or all those sieves which you are declaring to be covers, then JC is of course a partially ordered set under inclusion. What this says is that it's upward closed, right? Upwards closed is the correct term, right? It's a filter, okay. I don't exactly remember the definition of a filter, but okay. So everything that is above some admissible sieve is again admissible. This is what we need to show. So how do we show that R is in JC? Just quickly if you have access to the notes, just quickly look at the 3 axioms of a Grothendieck topology. Which of those axioms do you think will be relevant here? So we want to show that something is a covering sieve. Something belongs to JC. So which axiom should be relevant here? What do you think? Which axiom should be relevant here? The transitivity axiom, right? The third axiom should be relevant here. That is what allows us to show that something is a covering sieve. So what is the transitivity axiom? It says that suppose you already know that something is covering. Suppose S is a covering sieve. Suppose S is in JC. And suppose R is a sieve on C, which has this property that for every arrow F in S. So forget the problem for the time being. What does the third property say? It says that suppose S is in JC and R is a sieve on C, such that for every arrow F from, let's say, D to C in S, if you look at the pullback of this sieve under F, which is F star R, pullback of R under F, what is this? This is by definition all arrows G such that codomain of G is equal to D. So all arrows going into D with G composed, is it G composed F or F composed G? First comes G, yeah, so with F composed G in R. This is what the pullback sieve is. And you can prove actually that for any sieve and for every arrow, so for any sieve on some object C and for any arrow going with codomain C, with target C, the pullback sieve, the pullback is again under that arrow is again a sieve on the domain of the arrow. So yeah, so what does the transitivity axiom say? It says that suppose S is in JC and R is a sieve on C, such that for all arrows F in S, F star R is in JD. It's a sieve on D, and it should be, if it is in JD for every arrow F, then R is in JC. And this is something which we want to show here, right? We want to show that R is in JC. So we better first pick up some covering sieve S, right, for our object C and show this property. But we are already given some particular S. We are already given some S which is in JC, right? So why not work with that one? So let S in JC. Oh, I'm sorry. S is already given to us. So we can. So what we want to show is that for every arrow F in S. So S is a sieve on C, and a sieve by definition is a set of arrows with target C, which is closed under precompositions, right? So let F from D to C be an arrow in S. Now when we say that this is an arrow in S and S is contained in the sieve R, we already know that this is an arrow in R, right? So look at F star of D. F star of R. Let's write down the definition again. So F star of R is some arrow G from some object to D. So an arrow with target object D and source object anything, such that F compose G is in R, right? What do you think F star R is? We want to show F star R is in JD. What do you think F star R should be? So here again we need to prove that something is in JD. Do you know something that is always in J of an object for every object from the axioms. Do we know of a say? Yeah, you can say isomorphisms, but I mean in the language of the way, I mean in the way that it was entirely, I mean the notion of a grothendric topology was defined. If you just look at the axioms, what axiom guarantees existence or guarantees non-emptiness? The presence of the maximal sieve, right? The maximal sieve on an object is the sieve of all arrows with target being that object. So if we can show that f star r is actually the maximal sieve or has all arrows with target D, we are done. Now is it not the case? Why is f star r why is f star r the class of the set of all arrows with target D? So f is an arrow in S. This is our hint. So I'll erase this. We want to show f star r is in JD. We in fact claim that f star r is the maximal sieve on D. So think about this. D to C we have taken some f. F has source T and target C. Yes. Why? I mean, what is that one line that we need to mention? So f is an arrow in S. So what can we say? F is an arrow in S. So for any G, F compose G is in S, but that doesn't guarantee that F star R is the maximal sieve. Oh, okay. Sorry, I'm sorry. What you are trying to say is this. Yeah, I misinterpreted. What you are saying is this, that F is an arrow in S, F star R. I mean, if you take any arbitrary arrow from this object to D, right, then if you compose it with F, because S is a sieve, F is an arrow in S, F composed with this arbitrary arrow is in S. And if it is in S, since S is contained in R, it is also contained in R, right? That is what you are saying. Yeah. Okay. So F star R, yeah. So let's say, notice that for all G from an object to D, for all morphisms G with target D, F compose G is in S. Because S is a sieve, it's closed under precompositions, right? So F compose G is in S, which is contained in R. So F star R is the class of all arrows with codomain C, or let's say maximal sieve. F star R is exactly the maximal sieve on D. So F star R is in JD for all F from D to C in S by the transitivity axiom for a Grothendieck topology, it follows that. This is exactly what the transitivity axiom says. It follows that if star R, it follows that R is in JC, and we are done. Okay. So JC is upwards closed, or as Pranay already said, it's a filter. Okay, let's move on to, by the way, I just wanted to ask one thing. I can already see this, but yeah, was this property of a presheaf category proven in the sessions that every presheaf is a co-limit of representables? Okay, so how was it done? Can you give me the rough proof? Okay. Okay. Yes. Okay. Yes, correct. So what you do is you take, suppose, a presheaf F. What the claim is that this is equal to the co-limit of the category of elements, which is traditionally denoted by integral F to C pi to C of, oh no reason. It is also sometimes written as ELTF. None that I know of, at least. Okay, so pi, and this is your Yoneda functor Y, and the claim is that this is exactly the co-limit. How would you prove this? Just a rough idea. Okay, so you can prove this directly. What you have is, you can show that F forms a cocon on this diagram. Firstly, this is what you need to show, and then what you show is it is a universal cocon on this diagram. That is, it is a co-limit of this diagram, and then the proof is over. If you want to look at the proof in details, you can look at Maclean and Mordaek's book, or you can also have a look at what is that? I think Henderson does this. Not Henderson, I don't exactly remember, but yeah, this is what I'm trying to say, is that this is straightforward to prove. Once you guess what your diagram should be, once you guess what your shape category should be, and what your diagram should be in your presheaf category of that shape category, this can directly be proved. Okay, now why am I mentioning this all of a sudden is this thing is actually very important. Can you give me some interpretation of this result? What does it say? When you say that every presheaf is a co-limit of representables, what does it say? What does it essentially say? Okay, so what it says is that you can approximate all presheafs. I'm essentially just restating what the statement says. Every arbitrary presheaf on a small category can be approximated in terms of representables, right? Now, the reason why is this so important is that in certain situations, what you might have to do is, let's say for example, show the existence of some left adjoint. Let's say I'll give you a very small example in brief. I mean, this is the idea, this is the way it is used. So you recall the category of simplicial sets, right, which is this pre-sheaf category, and you recall the category of topological spaces. From top to this, you have an obvious functor, which is the singular simplicial set functor, right? And this functor actually has a left adjoint, which is the geometric realization, classically denoted like this. This functor is a left adjoint. Sometimes it happens that, I mean, expressing this left adjoint is a bit difficult sometimes. So what you can do is, first define this on all representables. Okay, so define, I mean, I won't get into the details, but define this on representables. And how is it defined? What is exactly a representable here in this pre-sheaf category? It's a functor from, it's a functor like this, right? An object in delta is exactly box n. So a representable functor is exactly delta of cap comma box n, functor represented by box n. This, once you take the geometric or try to define the geometric relation, this should be some topological space, and this is defined to be the topological n simplex. So what you do is you fix, you look at Rn plus 1, and in each axis you take one unit and look at all those points. So 1 0 0 0 0 1 0 0 0 0 1 0 0. Look at the convex hull of that. That is the topological n simplex. Now the interesting thing is, because this is a pre-sheaf category, and we know that representables can approximate all pre-sheaves. So to define this, the geometric realization of a simplicial set, what you do is define it to be the geometric realization of the co-limit, of that particular co-limit. So look at the category of elements of X, take the projection functor to delta, then use the Yoneda embedding to get to the category of simplicial sets. So you have that particular diagram, Y composed pi. Your shape category is the category of elements of X. Yeah. You want X, we know X is isomorphic to this, so why not just define geometric relation to be equal to the geometric relation of this? But since we want the geometric relation to be a left adjoint, it preserves co-limits. So why not define it as this? This is exactly a diagram of representables. Y composed pi is exactly a diagram of representables because you are using the Yoneda functor at the end. So this is not exactly, this is not the precise notation, but you understand this n's are coming from the shape category. So what you ultimately have is some co-limit of topological n simplices in top. So why not define the geometric relation of X to be this? So this is just one example. But this is the idea. This is the essential way in which that result is actually used. Okay. So this is what I wanted to say. Yeah. Yeah. Okay. Let's quickly get to this one. Suppose E is an elementary topos. We now know what an elementary topos is. What we want to show that is every morphism from X to 0. Suppose 0 denotes the initial object of X, of the topos. What we want to show is that every morphism X to 0 is an isomorphism. So if this happens, so what is an initial object? If we recall quickly, an initial object is some object in our category such that for every arbitrary object in our category, there is a unique morphism from the initial object to that arbitrary object. That's all. That is all that an initial object is. Now, if an initial object satisfies this property in addition, that for every morphism X to 0, every morphism X to 0 is an isomorphism, or whenever you take a morphism X to 0, X will be isomorphic to 0, etc. Whenever something like this happens, the initial object is referred to as a strict initial object, in the sense that it doesn't admit any non-trivial maps to it. That is why it's sometimes called a strict initial object if this additional thing happens. So what we want to show is that in an elementary topos, every initial object is strict. So how do you show this? I mean, just a rough idea. So try to think about the category of sets. What is the initial object in the category of sets? Yeah, empty set or OE, not phi, because OE is the Danish letter. So take the empty set. Now, yeah, OE, it's OE. Yeah, so what happens? So if you write this sentence for the category of sets, every function x to the empty set is an isomorphism, and that is obviously true, because by definition of a function, you can only have if you take a function whose target is empty set, then its domain has to be empty set, right? So that has to be the identity only. So something, and again, if you look, think about the internal language of a topos, something like this, if it happens for the category of sets, it's most likely to happen for an arbitrary elementary topos as well. And that is what we want to show. So every morphism x to 0 is an isomorphism. Sometimes people, whenever algebraic geometers do algebraic geometry and they work with a lot of sheaves and all these things, what they usually do sometimes is think about, it's not that everyone knows the internal language of a topos in proper terms, but to guess a property or to try to prove a property, one can essentially think about sets and functions and then try to show it using some tools, etc. So this is just an example or an instance of what we want to do here as well. So every morphism x to 0 is an isomorphism. How do we show this? So E is an elementary topos, right? Do we know something about this? X cross 0 should be 0. Why? Yes. No, right? No, that's not what Cartesian closeness means. It means that this functor has a right adjoint, right? Taking products with x has a right adjoint which is power x. That is what it says, right? Yeah, so now can we say that x cross 0 should be isomorphic to 0? Why? Because okay, yes. So what you are saying, so let me write it. So what you are taking is 0 in place of x, right? So you are looking at this functor, applying this on x. That is what you are saying, right? So E is notation, E of x cross 0 comma, okay, okay, x cross 0 comma what? Okay, let's put 0 here. This is in bijection with E of, so x will stay here, right? because the functor bar cross 0 is getting applied to 0, getting applied to x. So the functor is bar cross 0, so x will stay here, right? Because you are looking at this adjunction. Yeah, so x comma 0 power 0. So why does that do the trick? Okay, so I mean you are on the right track. I'll just quickly mention this. What do you want to show? You want to show x cross 0 is terminal, right? I mean initial. So there is supposed to be exactly one arrow from x cross 0 to an arbitrary object. So take an arbitrary object A, right? So E of x cross 0 comma A, this is what we want to find out, right? What is E of x cross 0 comma A? This is isomorphic to E of 0 comma. So let's think. Yeah, it's okay. So let's think about this functor bar cross x. So 0 will stay here, and on A you have to now apply the power functor x. 0 is initial, so this is a singleton, right? Done. And even more simply, this functor. So since this is obviously true, because since this functor from E to E is a left adjoint and an initial object is a co-limit. I mean that is what we proved just now. That left adjoints will preserve initial objects. 0 is a co-limit, so it will automatically be preserved, right? Now, what we claim is, so we want to show x is isomorphic to 0 first, and then we will show that this morphism x to 0 that we have taken is an isomorphism. So now, x cross 0 is already isomorphic to 0. We can just try to show that x cross 0 is isomorphic to x as well. Take x cross 0, take x. So from x cross 0 to x, we already have our projection map pi, right? We want to show that pi is exactly an isomorphism. So note that x cross 0, this is what we want to show is, I mean, we know that x cross 0 is already initial. So there is exactly one arrow from x cross 0 to x. We already have one, which is pi. So that has to be that arrow. We want to show that x cross 0 is isomorphic to x, right? So if that happens, that means pi has to be an isomorphism. So which means that pi, we need to construct an inverse, show that an inverse arrow for pi exists. So we want a map from x to x cross 0. What map should we take? What map should we take here? Yeah. What map should we take? X cross 0 is a product, right? It's a limit. So we can use some universal property of products, right? We can use the universal property of products. Yes. So there exists a unique morphism x to x cross 0 such that, so what I want essentially is a morphism from x to x and a morphism from x to 0. What morphism from x to x should we take? Obviously ix. And what morphism from x to 0 should we take? Yes, exactly. By the universal property of products, products are limits. So x cross 0 is a we will form a limit cone on this discrete diagram, right? Which means that for every arbitrary cone will factor uniquely through the limit cone, through x cross 0. So which means that, so limits are terminal, so in some category, so there is a unique arrow from x to x cross 0, which makes this commute pi x. Let's say this is pi x. Let's say this is pi 0. Very bad notation, but okay. Pi x. This commutes. And let's denote this by 1x comma f. So what do we know about this morphism? From the diagram we know that 1x comma f. So pi x composed with 1x comma f is 1x. This we know. What do we want to show? We want to show that pi x is an isomorphism with inverse 1x comma f. So we want to show that the other composition is also identity. Now 1x comma f composed with pi x. This is because it's, I mean, this is an arrow from x cross 0 to x cross 0, right? Right? This is supposed to be the identity. Why? I mean, this is clear now. Why is this going to be the identity? What do you think? We have already shown that x cross 0 is isomorphic to the initial object. So it's an initial object in our category, right? And from initial object to any arbitrary object, there has to exist exactly one arrow. Now we already know an arrow exists from x cross 0 to x cross 0, which is identity. So this has to be equal to identity. Equal to 1 on x cross 0, as x cross 0 is initial in our category. So we have proved that pi x and 1x comma f are inverses of each other. So pi x is an isomorphism x cross 0 to x. Proved. And we already know that x cross 0 is isomorphic to 0. This one was known, right? So what can we say now? 0. X is isomorphic to 0. So in particular, this means that x is the initial object. And if x is an initial object in our category, why does that immediately imply that the arbitrary arrow f from x to 0 is an isomorphism? So yeah, so what have we achieved so far? We have this elementary topos, and we have shown that if you take if there is an arbitrary arrow f from x to 0, then we have shown that x is isomorphic to 0. We haven't really proven that f is an isomorphism. But what I am saying is, once you have proved that x is isomorphic to 0, it immediately follows that the arbitrary morphism f from x to 0 is an isomorphism. Why is this? So we have x is isomorphic to 0. It immediately follows that f from x to 0 is an isomorphism. Why? Why is this morphism an isomorphism? Because x is isomorphic to 0, we know that x is an initial object, right? Now from x to 0, there has to exist exactly one arrow. From 0 to x, there will exist exactly one arrow, right? If you compose them from x to x, you should get some arrow, and x is initial means that the only arrow x to x is identity. Similarly, composing the two arrows in the other order gives you an arrow 0 to 0. 0 is initial, there is exactly one arrow 0 to 0 identity. So both compositions are identities, so f is an isomorphism as x and 0 I'll just mention as x and 0 are both initial. Done. So this is really interesting. I mean, at least we already know that toposes are very, I mean, there is this, so there is this parallel between the algebraic world and this geometric world. So for algebraic world, the right notions of categories are abelian categories and Grothendieck categories. For the geometric world, the right notion or the right categories to work with are exactly Grothendieck toposes. And many things are parallel between them. I mean, if you look at the Girard's axioms, characterizing axioms, they are very similar to how one defines axioms for Grothendieck categories and abelian categories. There are many other similarities. We know that we have already proven last week or last week that in an abelian category, pullbacks of epimorphisms are epimorphisms. And I'm sure that it was mentioned this week that in a topos as well, in an elementary topos as well, pullbacks of epimorphisms are actually epimorphisms. So there are many similarities between these two worlds, the algebraic world and the geometric world. I mean, even though there's there's no established rigorous connection or framework, but I mean that's the best kind of, I mean, mathematics is, that's the best kind of thing that you can have, right? You don't have some formal framework, but still you are suspecting that some connections exist. Right, so, and there are many other similar properties as well for Grothendieck toposes and Grothendieck categories. Grothendieck categories are localizations. Sorry, only one. Yes. Okay. What do you think? So if 0 happens to be the 0 object in this topos, we have already shown that since it's an elementary topos, x cross 0 is isomorphic to 0, right? Now 0 is an initial object, x cross 0 is an initial object. Since x cross 0 is isomorphic to 0, 0 being terminal also implies x cross 0 is terminal. So that means x cross 0 is also the 0 object, right? So, I mean, what exactly do you want now? Are you asking what happens to the topos if this happens? Okay. What is isomorphic to my original set? Okay. Yeah. Are you asking whether? Okay, continue. I'm sorry. Yeah, continue. Yes. Yes, that's always true for any terminal object, right? You can prove that if one is a terminal object, then and products exist, finite products exist, x cross 1 is isomorphic to x always. That's always true in any category. Yes, if that happens, then the topos will only contain one object, which is 0. Is that your question? A topos cannot be? Yes, you cannot put an abelian structure. I mean, unless it's the trivial topos, you cannot put an abelian structure on a topos. In fact, I mean it's understood, right? An abelian category can never have a zero object unless it's too. Can never have a subobject classifier unless it's too trivial, right? It's the same reason why the category of abelian groups doesn't have a subobject classifier. It's the same reason, because the terminal object is exactly the zero object. It has it is also an initial object as well. That is what creates all the problems. So if this happens, if 0 is a zero object, then x cross 0 is isomorphic to 0. I'm sorry, something is wrong, something is off. X cross 0 is isomorphic to 0. Did we prove that? We didn't prove that, right? X cross 0 will be isomorphic to x. This is known. Sorry. X cross 0 will also be isomorphic. We already proved that. We don't need existence of a map from x to 0 for that. X cross 0 is always isomorphic to 0. Right, we did prove that. So the x is isomorphic to 0, so the topos will be trivial. It's the same thing for what happens, for example, if you take in a ring, if you assume 1 is equal to 0, the ring is the trivial ring. Okay. And next, what you need to prove is that every morphism from 0 to B is a monomorphism. Why is this the case? Every morphism 0 to B is a monomorphism. Again, looking back at sets, any arrow from empty set to any function from empty set to B is injective, obviously, vacuously. So okay, so take two morphisms, let's say PQ from some object to 0. Yeah. Okay, by the previous problem, P and Q are isomorphic. In fact, they are equal, because existence of some morphism from some object to 0 implies that that object is initial, is isomorphic to 0, is initial. So P is equal to Q. Yeah. Let's say T maybe, such that, so take two morphisms P and Q. The first part of the argument that you give, we'll mention that at the end, such that TP is equal to TQ. Suppose this holds. So by previous problem, regardless or independent of our T, since this Hom set is non-empty, there is at least one arrow from this to 0. So this object is automatically isomorphic to 0, is the initial object. So since this is initial, P is equal to Q, and we are done. So what we didn't really use was this part, TP is equal to TQ, but that's okay, right? What you essentially want to prove is that T should be left cancelable. T should be left cancelable, yeah. So whenever you have TP equal to TQ, T can be cancelled. You should get P equal to Q, and that is what we have, P is equal to Q. Okay. So that means that T is a monomorphism. It doesn't matter, we didn't use this hypothesis TP equal to TQ. This will hold for all such PQs, right? But in particular, this holds for all PQs such that TP is equal to TQ. And that is what we want. So T0 to B is a monomorphism. Done. Let's quickly move to the last problem. Okay, so here again we'll not really be concerned about sheaves on grothending sites, because I believe that's not examinable, but we know we can talk about sheaves on topological spaces, and usually we talk about sheaves of sets on topological spaces. But what this problem essentially does for us is that we can now talk about sheaves with values in any category. So for example, one can, in algebraic geometry, people talk about sheaves of let's say abelian groups or rings or vector spaces. I don't know if vector spaces are also looked at, but certainly abelian groups and rings are concerned. So only requirement that we want here is that D be a category which has all small products, and then we can entirely formulate the definition of a sheaf on X with values in D. And that is our first problem. What we want to do is formulate a definition of a sheaf on X with values in D. So before that, let us quickly recall what the definition of a sheaf on a topological space X is with values in sets. I mean a sheaf of sets. Values in the values being objects of the category set, that is values being sets. So recall that a pre-sheaf, so this is recall, we want to, so this is the idea, this is the way things are defined in category theory. You have some definition, probably that definition involves elements, something which category theory is not really concerned about. So try to express it in an arrow theoretic form, and then once you have done that, you can entirely define it in an abstract category. So a pre-sheaf F from X. So what is a pre-sheaf on X, by the way? It's a pre-sheaf on the category OX, right? Of OX is the partially ordered set of open sets, so it's a category. So take a pre-sheaf on OX. So a pre-sheaf F from OX up to set. By the way, this is just a question since you are into order theory. OX is a partially ordered set that we know. OX is also a lattice that we know. Is there some more structure? I see. So you are mentioning sometime that frames and locales are duals of each other. Yes. Oh, so frames are something. So arbitrary, it has arbitrary meets. Joints. That is what you are saying. Ah, I see. So OX is a frame, or OX op therefore is a. I'm sorry. I think I've confused. OX is a frame, but that doesn't mean OX op is a local. What you were saying some time back was the category of frames is dual to the category of locals, right? Yeah. But that doesn't, that certainly doesn't mean. What I'm trying to ask is, what is a local then? It's just an object in the category of, it's the same as a frame. That is what you are saying. Just when you talk about morphisms, they are different. Okay. So that, okay, frames are algebraic in nature, locales are geometric. In fact, I think this local picture, okay, we can talk about this later. Yeah. Okay. And that has been proved. Okay. So it's monadic over sets. Okay. Okay, yeah. So we take a presheaf F from OX up to set, and recall that this presheaf F is a sheaf if for every open cover ui I in I of u of some open set u in OX, what happens? What diagram is an equalizer diagram? Okay, so let's first write down the diagram. So if ui I in I, product of if ui intersection uj, right? I comma j in I cross I, and from this to this you have two maps, P and Q. We'll get what is P, by the way? P sends a family xi I in I to what? It sends it to what? Restricted to, right? That's the restriction map. So if you take u contained in V in OX, that means in the category OX you have an arrow u to V, right? Which means that in the category OX op you have an arrow V to U in OX op. And since F is a functor from OX op to set, that means what you have is, you can consider, I mean, the arrow to which this arrow gets mapped onto under F is now some arrow if V to FU, right? So what is this? So V contains U, FV to FU. So what the idea from geometry is that U, V are open sets. FU is thought of as the collection of some nice functions on U, right? Or sections of your presheaf, etc. So FV to FU, what is this map? This is sort of like a restriction map. That is why it's called res VU, and sends some x, some element x, which you think of as a function on V, to x restricted to U. This is the notation, right? So that is what this is. Xi restricted to UI intersection Uj. Yeah. And this is what P does. What does Q do? Sends it to restricted UI intersection Uj. This diagram has an equalizer. Of course, we are in the category of sets. Every parallel pair should have an equalizer, and the equalizer is FU, right? Together with this map E. What is this E? What does this do? Sends every x to, what is xi? X to x restricted to ui, right? I in I. Yeah, this is what this E map does. This is an equalizer in the category of sets. So to define maps, these maps P, Q and E, what we needed was elements, and we could get away with it because we are in the category of sets. But now the question comes is, what if the category of sets gets replaced by some abstract category D, which has all small products? So what essentially is the problem is basically to reformulate this definition entirely so that the maps P and Q can be defined in a categorical way, in an arrow-theoretic fashion. So this is our question now. So want to reformulate the definitions of E, P and Q in a category theoretic way, in an arrow theoretic way. Yes. Okay, that is one way to do that, but that is like an sort of an externalization. You understand what I mean? That really won't do much of a job, because if you look at maps from one to something, that's still, what should I say? I mean, for example, just have a look at the notion of a group object or a group internal to a category, right? So once you talk about an internal group in a category, one way to one property is that if you look at maps from 1 to G, that will have the structure of a group. Okay, I mean that's a property of a group object, but that is essentially externalizing the definition, right? You are still using elements, or you are still rather using sets, right? What we want essentially is some element free description, element free way of capturing this notion with these maps P, Q and E. That is what I am saying. There are various ways in which you can capture something category theoretically. Looking at generalized elements or looking at maps from one to something is one of them, but that doesn't really achieve the full. I mean, this is of course an open-ended question. There could be some other answer as well, but that approach really doesn't achieve what we want to do. Do you understand my point? We want to forget about sets. My question is there a way in which P can be defined? So of course it's understood that UI is there a way in which P can be defined entirely in terms of arrows? So what does P do? Sends xi to xi restricted to UI intersection uj. Note that the target of P is a product. The codomain of P is a product, so we can use some universal property, the universal property of a product here, right? So how should we do this? So to get a map to the product, what we need is a map to individual factors. So to define P, we need for each I0, J0, let's say in I cross I, morphism from what to what? From the product of FUIs I in I to FUI intersection UJ. The source category of F is OXOP. We can talk about intersections, etc. So F acting on intersection, this makes perfect sense because the intersection is an object in the source category of F. What we don't have right now is that the target category, that is the codomain category, is not set. We can't talk about elements really. So this will now be an object in D, this will be an object in D. But we can still define the map. What map should we take from this to this? What map should we take? There is a map. There is an obvious map which mimics this one. Okay, so that's the first step. Take the morphism. Yeah, you define this morphism to be as factoring through the projection. So if UI, if UI0, let's say, you have xi here, that gets restricted to xi restricted to UI intersection uj. So if take the projection, let's say projection, and from this to this you need something. What map can we take? There's an obvious map. There is an obvious place arrow. So UI intersection uj and UI0, uj0. UI0 intersection uj0 and UI0 have something. I mean there is some connection between them. In OX, UI intersection UI0 intersection UJ0 is contained in UI0, right? So there is an arrow in OX from UI0 intersection UJ0 to UI0, right? UI0 intersection UJ0 to UI0. This is the arrow corresponding to the inclusion. Now that means in OX op what you have is an arrow UI0 intersection UJ0. I mean from UI0 to this you have in OX op. Now F is a functor from OX op to D. So just look at the image of this arrow. Just look at that particular arrow in the codomain to which this arrow gets mapped onto. So just apply F on UI0. Here we are abusing notation a bit. Let's write it like this. Even though the functor F acts on the opposite category, not OX, but we'll still write this in OX. So by which we mean that it acts on the corresponding arrow in OX op. Okay, is it understood? So of course, if you apply F on an arrow in OX, then the image arrow will be in the in the other direction. So you get an arrow from FUI0 to FUI0 intersection UJ0. Take this composite morphism. This, by definition, this gives a unique map, unique morphism in D. Since this happens for every I0 J0, this gives a unique morphism in D from product FUI I in I to product I0, I comma J in I cross I, FUI intersection UJ, right? So let's call this P. This is our P. This is exactly what P is supposed to be. P is that unique morphism which makes a particular square commute, and this is a unique morphism making a particular square commute. Those two squares will be the same. We'll write everything, the full picture at the end. Similarly, define Q in the same way to mimic this definition. Similarly, define Q. To summarize, I'll just write, and now everything will be clear. To summarize, what you have is, you have FUI, product FUI, I in I. You have two arrows, PQ, product I comma J in I cross I, FUI intersection UJ. From this, P is the unique arrow which makes this square commute. Take the projection to FUI0. Take the projection to FUI0 intersection UJ0. You have this arrow which is F applied on the inclusion UI0 intersection UJ0 contained in UI0. Right? This commutes. P is that which makes this commute, and Q is that arrow, that morphism which makes this commute. Take projection to projection to FUJ0, right? From this you take projection to FUI0 intersection UJ0 again. And what is this? This is F applied to UI0 intersection UJ0 contained in UJ0. Right? This is what our Q is, right? Right? This is what Q does, right? Q sends every xi I in I to xj restricted to UI intersection uj. P sends every xi I in I to xi restricted to UI intersection uj. Right? So this is what P and Q is. And what should E be now? We claim that E should be the equalizer of this. Now how do we define E exactly? E can be defined by giving maps from FU to FUI0 for one for each I0, right? In I, what map should we take? Fu to Ui0. This is F applied on the inclusion Ui0 Ui, I mean U, right? This is F applied on Uj0 contained in U, right? I mean, to define E, we didn't need to write this as well. I mean, it's understood what this is. So let's write one line for that. Define E from the product, E from Fu, this is an object indeed, to the product object, product Fui, I in I, by, as the unique morphism induced by the family. So Fu to Fui 0, let's say I0 in I. What is this? This is F applied on the inclusion Ui0 contained in U. The direction will again flip if it's contravariant. So this is a family of arrows going into the factors, from Fu going into the factors. So there exists a unique arrow from Fu to the product, making certain small triangles commute, right? And that is what this arrow E is. E is that arrow, E is that arrow which makes this commute. Every small triangle commute. In particular, the two triangles that are present here, this one and this one, these two triangles are commuting. Okay. So this is what we have. So what can I say now? So I can say that a pre-sheaf F from OX op to D, this is a pre-sheaf of objects of D. When we say a pre-sheaf, just as we say a pre-sheaf of sets, a pre-sheaf of abelian groups, we'll say, of course, a pre-sheaf of objects of D on X, on the topological space X, is a sheaf if and only if the arrow E above is the equalizer of D, equalizer of P and Q, of the parallel pair P and Q of arrows in P and Q in D. Okay, where P, Q, and E have been defined in this way, such that this diagram commutes for every I0 and for every J0. To summarize, E, P, and Q are those unique morphisms such that this diagram, the diagram below commutes for every I0, J0 in I. Okay, or for every ordered pair I0, J0 in I. Is this okay? So I have entirely rephrased the definition of a sheaf now on a topological space, but taking values in an arbitrary category. So this covers sheaves of abelian groups, sheaves of rings, sheaves of objects of any abstract category. For example, you could, for instance, take some special partially ordered set as your category. And what you have is a sheaf of elements because your category is your single partially ordered set. So you have a sheaf of elements on a topological space, etc., etc. These are just some rough ideas, and we have only one part left, which is which is exactly a one line. So what does this say? Problem 2 says that, and this is true in general for any sheaf, which says that suppose F is a sheaf on a topological space X, then of course F acts on the empty set is open. F of empty set will be the terminal object of D. That is, sheaves always take empty set to terminal objects. Why do you think this is the case? So in a sense, yes, right. Yes. Yes. Yeah, but why? This is not true for any functor in general, right? Because there are functors which don't preserve terminal objects. They need not preserve terminal objects. But for if F is a sheaf, if F satisfies the sheaf condition, then this happens. So just look at this. Just look at this central diagram that we have. This is our sheaf condition, right? We want to show that F of empty set is 1. So why not just take U to be empty set? Now if you take U to be empty set, can you give me an open cover of the empty set? Itself is an open cover. Can you give me a more basic open cover? No, whole set cannot be open cover, right? Because union of whole set cannot be empty set. Some even more basic open cover. Huh? Yes, more basic than empty set. Empty set covers empty set, but can you give me an open cover of the empty set which is even more basic? We know that unions indexed over empty sets, empty unions are empty, right? I mean, if you take your index set, so what I mean is, suppose you write union I. Suppose the index set I is empty, then this union will be empty, right? So what I'm saying is, so observe that this is the empty set is an open cover. I mean, what should I say? The empty family is an open cover for the empty set. Okay, in fact, we can write it like this. Observe that UI, where I is in empty set, is an open cover for empty set. And just so that people don't get confused, I'll just write that this is empty family. Empty family. There are no members in it. So it's an open cover for empty set. Now what happens if we use this sheaf condition? What happens here? So since F is a sheaf on X, so you take product FUI, I in empty set. The index set is empty. What happens to this product? What is an empty product? Think of it like, no, empty product is not empty. Think of it like this. Think of your index set as a discrete category. Taking the limit of any diagram of this shape is exactly taking products. So taking it should be, yes, because why? Because so what is this product I in I of some objects AI, let's say. What is this? This is exactly the limit of a diagram of shape I in your category, where I is considered as a discrete category. What happens if I is empty? What happens to the limit? The limit is exactly the terminal object, right? So empty products are terminal objects. That is why when you sometimes say that suppose your category has an empty has finite products, that in particular implies that it has a terminal object, because terminal objects are exactly products indexed by empty family. Okay. So this is isomorphic to 1. From this to you take PQ to product FUI intersection UJ IJ in empty cross empty, which is empty. What happens to that product? What happens to that product? It's also the terminal. UI intersection UJ empty cross empty, which is empty. So this is also the terminal object 1. So you have arrows PQ here. What is the equalizer now? Let's say this is E. This is supposed to be empty set, F of empty set. That object has to be the equalizer. What is this equalizer? What is the equalizer of these two arrows? PQ 1 to 1. One is terminal. Obviously, because one is terminal. So what can you say? What should the equalizer be? What should the equalizer be of two equal arrows? It should be the identity, in fact, right? So 1 to 1, 1 on 1 is exactly the equalizer, equal to equalizer of P and Q. So E is an equalizer, 1 1 is an equalizer, means that there is an isomorphism from F of empty to 1, which makes the triangle commute. In particular, F of empty is isomorphic to 1. So F of empty is isomorphic to 1 for any sheaf F, for any D script D valued sheaf on F on X. Okay, so this solves the problem and ends what we wanted to do. Yeah, I just now remembered that we didn't still solve problem 1, but yeah, I'll put up a solution. I'll think about it. It's probably some minor change that needs to happen here. I'll put up a short solution. Write down a short solution. Yeah, and if you don't have any other questions, we can stop. Okay. I'll stop the record.